Okay, thanks for the introduction. So we continue this afternoon. We've seen the supervised learning this morning, so we'll continue with the other side this afternoon, the unsupervised way of learning from data. So the first question one may want to ask is, why doing unsupervised learning? Basically, why not using labels? That's the core question. Well, first answer, obviously, when you don't have labels, you don't use labels. So this may be the case when you want to do knowledge discovery, for example, to represent faces in a population of faces. You want to look, for example, for the variability in the faces, the determinants of these faces. Or, for example, as we do in medical applications, when you have a population of, for example, myocardial strain patterns, the deformation of the heart along the cycle, and you like to see the variability in a population. So in this case, you don't use labels and you want to represent your population based on these data. Second answer, is when you don't really trust your labels or you think they're not fully relevant to the problem you want to address. So as an example in medical applications, you may know or have the intuition that disease is not binary. One day you wake up and you do have a heart failure. No, it's more a continuum from healthy to disease, with several things that happen that modifies the trajectory of an individual from healthy to diseased and the severity of this. So these are two examples from reviews in heart failure. Like you see here, the evolution of a healthy heart that progressively changes its shape and maybe some deformation parameters to the pathological heart, to diseased heart. So in this case, it's a continuum, and it's better not use supervised techniques to represent this continuum. As an example, for example, we had a clinician from Cardiff who came to us and said, I want to study this syndrome, which is heart failure with preserved ejection fraction. Basically, these are patients that have symptoms of heart failure, but still a normal ejection. And basically, the labels that are used in the clinic are just categorizing this, while it's actually, as I said before, a continuum. So the clinician came to us saying, I'd like a better representation of my data to better understand what happens in this continuum. And we've managed to kind of use unsupervised learning techniques from many cardiac imaging descriptors to kind of have a rather like healthy zone, a disease zone, and have a look at the transition zone and whether other patients could be mapped to this. The last answer to this question, why not using labels, maybe just because having a supervised way of thinking for the clinical problem may be limited. So I'm taking an example, the field of cardiac resynchronization therapy, which is for patients that have cardiac dysynchrony, a specific type of dysynchrony with specific selection criterion. And these patients are equipped with a pacemaker that is supposed to resynchronize the heart, to make it contract synchronously. And patients are selected, so in a supervised way. And there are still 1/3 of patients for which it doesn't work, which is very problematic. So these are the kind of abnormalities you see, like kind of dysynchrony that happens. Do you see my cursor? Yeah. A kind of desynchronous pattern that happens at the beginning of the cycle. And the point with this supervised way of thinking is that, yes, 1/3 of patients do not respond to therapy, so they shouldn't be equipped. And the same way, we've tried to represent this data in an unsupervised way, so using a lot of cardiac imaging descriptors. We came to an unsupervised representation, like a cloud. I'll go further on this. And try to find, instead of saying who will respond or who will not respond, try to find clusters, groups of subjects that behave similarly. And then maybe inside there are responders and maybe there are non-responders, but look at the risk between these clusters. And what we've seen is that in some, there's a high cluster with high risk, there's a cluster with very low risk, and maybe this is a better way of understanding subgroups that may respond to therapy. Okay. So basically, why not using labels is maybe you want to have a different look on your data. And this obviously depends on what's the endpoint of the application. So I've tried to structure a bit the speech around this. The first part of the speech will be about identifying subgroups in a database, identifying similar trends, and in this case, we fell under the umbrella of clustering. There's a second aspect I'd like to cover is detect outliers, detect novelty, unexpected values, and in this case, it falls under the umbrella of outliers detection. And then I'll go a bit further on what is great for the moment. So for clustering, basically you have a population and you would like to find, without being influenced by a ground truth label, you would like to find patterns of similar cases, subgroups of similar trends. So in the left case here, it may be obvious that we do have 3 clusters. On the data on the right, maybe there are 3 clusters, maybe I could have drawn 5 or 8, I don't know. So here's the key point about this. So first algorithm to perform clustering, which is very popular, is k-means. K-means has a main parameter, which is k, the number of clusters. It's a hyperparameter. Basically, you'd like to partition your data into k clusters. And the way it works, it tries to minimize the variance inside each cluster. So here's the function to minimize. Basically, inside each cluster, it looks for the distance of each sample, v, to the centroid of each cluster. So basically, the consistency within each cluster. So here's the way it works. Below, if we have this kind of data, we could launch the algorithm saying k equals 3 and have this apparently good result, but we could launch the same algorithm with k equals 4 or 5, etc., and have different results. So the algorithm to perform this is basically a first initialization step, and then iterations that try to refine the position of the centroids. So basically, you start by initializing the centroids. Either you have a better partition from the beginning, or you pick randomly 2 samples. Then you assign each sample to its nearest centroid. So basically, if you see on the scheme here, I've picked 2 samples randomly, and the closest samples to the blue are labeled blue. The closest samples to the red are labeled red. And then you update centroids as the average of these labeled clusters. So by an iterative process, normally it should converge to the 2 clusters you'd like to find. So some comments. Obviously, this is based on random initializations. It may converge to a local minimum. So if you want to have a stable result, you need several resources of your algorithm. You end up with simple cluster boundaries, straight lines, or a bit better. And obviously, it's not directly applicable in high-dimensional data. So if you do have as input images, for example, digits images of 8 by 8, so these are 64 dimensions for each sample, you could not, or you may not directly launch this, and you may want to reduce the dimensionality of the data first. So I'll come back to dimensionality reduction afterwards. So some applications in cardiac imaging or in medical imaging. In the clinic, there are sometimes these kind of electrical activation patterns that are obtained by having a catheter that touches the cardiac wall during the operation. And there may be some spots here of where the catheter leads is activating the pacing of the heart. So you may want to use this kind of algorithm, k-means, to find the spots of electrical activation immediately. So in this case, k equals 2, it's very easy. I come back to the other application on cardiac resynchronization therapy, where people I've worked with ended up with many variables represented as this kind of cloud, and we actually wanted to find different clusters related to different risks in the patients. So what was used here again was clustering with different number of clusters. We tried 3, 4, 5, etc., with different evaluations to find the optimal number of clusters in this. So another model to perform clustering is Gaussian mixture model. So basically you have the idea that given a distribution like this, we'll try to fit two Gaussians to the data. So actually the parameters, there are these ones, the mean of each Gaussian, the covariance of each Gaussian, so basically the definition of each Gaussian, and the weight you give to the mixture. Either you want one to be very dominating the other or not. So an example, like the red Gaussian is mixed with the blue Gaussian with equal coefficients, and you have this mixture in black curve here. So the assumption is that your samples are generated from a mixture of a given number of Gaussians. So it's kind of generalization of the previous algorithm of k-means. And what you'd like to consider is the probability at each sample, which is basically the weighted sum, so P, K, E, here are some weights, of a probability distribution of a Gaussian that is centered on this mean with this kind of covariance. Okay? So the algorithm, given this probabilistic view on it, is the expectation maximization. It starts again with an initialization randomly, or you could use, for example, you could pre-launch the k-means on this data and go further with the Gaussian mixture. And then the iteration is about computing probabilities and maximizing likelihood to update the parameters. So basically at each point you have to compute the probability of having this cluster given the sample. And updating the parameters is the next step up to which you iterate. And what you look for is updating the weights as the average of the probabilities for each samples, and updating the average of each cluster, okay, a weighted sum of this, and the covariance. So here's an example I've launched on this kind of data. It's initialized with these two centroids. The initial guess with the two Gaussians, and you see that, like, maybe it's not clear on the screen, fully clear, but you see that the points are not fully labeled blue or red. It goes from blue to red up to violet in the middle. So you see these probability changes, okay? And across iterations, after several iterations, in this case it took 22 iterations, you find the two desired distributions, the desired clusters. So an example on medical application, imagine you register the heart rate of some subjects during one day. You have this, the variations of the heart rate during the whole day. So it's better to look at this in terms of histogram, the distribution of the heart rate across the day. And you may see that there's a peak here, maybe kind of rest period, and all the peaks that corresponds to other moments during the day, I don't know. And a Gaussian mixture would be a fit like this up to this histogram distribution. Okay? So this is 1D version of this simple problem, but you may go 2D, etc. Then another algorithm on clustering, maybe a bit less classical, but very popular recently. I'll show some applications, which is called hierarchical clustering. The idea is to look at the problem either in an agglomerating way or in a dividing way. So agglomerate means you start by each sample is a cluster, and then you try to build a hierarchy into which you merge progressively, samples together. Okay? Divide is you start with a single cluster that picks all your samples, and when you go through the hierarchy, then you try to divide progressively your clusters. So a simple example I took from Wikipedia. Imagine you have like these 6 samples, A, B, C, D, F. You see that given the Euclidean distance between these different samples, A is very far from the others, B and C are a bit grouped, and D, E, F are kind of close. So if you start by the agglomerate strategy, each sample is a cluster, so you have A, B, C, D, E, F that are separated, and then you start merging them up to different levels, different thresholds of your Euclidean distance, and you see that obviously B and C are quickly aggregated, D and E together, so this is the first level in hierarchy. Then D, E, F are put together, and then up to the whole set of observations. Okay, so this is very intuitive, and it was recently used in 2 papers alike that looked for phenotyping. So sorry, there's a lot of cardiac applications because it's my field of research. So people tried to went out with phenotypes of heart failure with reduced ejection or with preserved ejection. So what they did in these 2 separate papers, they picked a lot of clinical variables. So I don't know the list of them. And they picked a whole population, and they tried this kind of clustering hierarchically to find out subgroups of variables and subgroups, clusters of variables and clusters of subjects that that behave similarly. So here, these kind of maps just express subgroups of variables and people that behave similarly. So you may see that here there's a kind of red spot that may mean something for the potential application, kind of blue spot that may mean another thing, etc. So this much more for knowledge discovery. So all this was about finding clusters, but when you fit a distribution to some data, you may also want to use it for another thing, which is finding outliers, unexpected cases. So 2 examples. A cluster of this, you fit kind of a spherical circular distribution or symmetric distribution, and you see that there's a lot of outliers out there. But you may also fit more complex distributions to this to find outliers. So I won't go too much into details, but that's very, basically there are 2 steps of this. First, fitting a distribution, and then looking at the decision function to come out with the distance that characterizes your outliers. So a very popular one is the Mahalanobis Distance, which is basically the distance of each sample to the mean of the distribution, divided by the variance. So if you have a 1D case, it's basically the distance to the mean divided by the standard deviation. Here's a version in 2D or more dimensions, but basically it's the same thing. So as you have a probability distribution, you may also come out with significance value performing statistical tests, p-value, etc. So some examples. What we did some years ago is still for the heart. If you have a population of healthy hearts that you bring to the same system of anatomy, of spatial temporal coordinates, you may end up with a distribution of what is, for example, normal motion for a healthy heart with an average and a variance. And if you are able to map new cases to this reference and compute a statistical distance, as I said before, the Mahalanobis distance, you may spot some abnormalities that may be specific to a given pathology. And we use this for characterizing the response to the resynchronization therapy I've shown before. Another application, another example of going further with outliers detection is some work that Carol, who presented first, she worked on. She looked at, with some students, the robustness of detecting outliers in epilepsy applications with MRI. And basically with some standard algorithms, you may be very sensitive in the fit of the distribution to some outliers, and they try to robustify this detection of outliers, as you see here. Okay, so clustering outliers detection is maybe what we'd like to do in the end, but you see that much before, the key step is finding a common data representation to to perform this clustering and to have this cloud of points that separates the data. And I'll go through these 3 steps. The first one is trying to find this representation that is convenient for representing the data and that may be with lower amount of dimensions. So I'll explain this a bit better. Then the second step is, the second important point I would like to discuss is having a notion of statistical distance into this space, and then I'll go into the concept of manifold learning and what it means. And then I'll go through how to exploit this case and maybe go from the initial input space to this convenient representation with the problematic of encoding and decoding throughout these spaces. So the key thing, and it's a whole field of research, is called representation learning or representation. So the basic idea, the objective, is to find a representation that better represents the data, possibly with a lower amount of dimensions, and in our case, without using labels, so unsupervised. So as inputs, you may have a single descriptor which is of high dimension. For example, the cardiac motion, but at each point of the myocardium, at each point of the heart wall. So many points, but a single descriptor. Or you may have multiple scalars, for example, the age of the patient, the weight, the size of the heart, or many things. Or you may have a mix of them, which is often what exists in clinical acquisitions. You may have a mixture of high-dimensional descriptors, multiple ones, extracted from clinical data. And what you'd like to find is an output representation that better represents your data with lower amount of dimensions. So there's 3 steps to distinguish. The first one is finding the embedding, so mapping from the input space to the output space. The second thing is having thoughts about what is your lower dimensional space, which specific structure, maybe there's something which called manifold, or maybe it's just a latent space that is convenient to represent your data. And then the last step is reconstructing your data from the low dimensional space to the input space of data. Okay? So the key question, hope you see it, is which space to work on. Basically, do you want to exploit distances in the low dimensional space, so on the bottom, or would you like to see cases in your original data spaces? Maybe these kind of coordinates are a bit hard to interpret, and you better interpret cardiac shapes or brain shapes. So first question is, do you have an intuition about the structure of your data space? So I come back to this very talkative example. A set of faces from a population, so different individuals and many faces per subject. And you may find a representation where each face is a sample here in this cloud. So this cloud may have an average and a variance. And you may think that if I take a picture of a face like this and a face like this and I do the average of these faces, classical average will be not a face anymore. It will be something, a mixed face, which is like this. So you may want to think about the structure of your data space, which may not be linear. So as explained here, as illustrated here, this half donut may be the space of all the faces for this individual. And if you compute the average of all these faces in a standard way, you may go here to the point B, which is out of your space. So it's this kind of face. It's not a face anymore. If you try to behave along this nonlinear space, so if you use relevant techniques for this, you may find this face, which is actually intermediate in these faces. Okay? So regarding the structure of this data space, you need to find a lower number of dimensions that encode high-dimensional data variations. So if you want, for example, to exploit afterwards the meaning of your data space, you may want to look, for example, if I draw a straight line across this data space, I may want to see the evolution of these digits across these lines. Do they vary in shape? Do they vary in size, etc.? So the key idea behind this is the structure of the data. So I'm sorry if it's temporally a bit more complex, but I would like to provide you the intuition about this. So you may hypothesize that your data belongs to a specific nonlinear space, which is called a manifold. So manifold examples are, for example, the sphere, the Earth. It's basically a space, high dimensional or some dimensions, that's near each sample. So if I pick a point on the Earth, it resembles to a Euclidean space. So basically here the Earth is in 3D, but if I look very closely, our location, around this point, it's a 2D map, a planar map. So that's the definition of a manifold. Okay, so some examples, lines, circles are one-dimensional manifolds. A plane, a sphere, a surface, they can be locally matched to a plane, so they are manifolds of dimension 2. And brain images, cardiac shapes, etc., they are manifolds of unknown dimensions, we don't know. So in some cases, there's no need for learning. People worked a lot on this, and in some cases, you know the structure of your manifold. You know you want to do distance computations by respecting this space, and actually there are mathematical tools to navigate between your nonlinear space and a tangent space, a Euclidean space, into which you can do statistics. So there are mappings that are called log exponential mappings. I won't enter into detail, but here's the reference. So why is this important? Imagine you do a diffusion tensor, or you work with strain tensors, and you'd like to interpolate between the bottom left corner and the top right corner, and you may want to see the graduation between this. If you do this linearly, you have this kind of diffusion tensors. If you do this by respecting your nonlinear space, you have a completely different result. So which one is correct? In this case, we know mathematically this one is correct, but you see the consequences it could have for the medical application. The same is often used for image registration. You may do image registration not respecting this space, and there's a whole framework, I won't enter into detail, of having specific transformations that are defined according to this space. Nonetheless, in most of our applications, we don't know this specific, we just hypothesize that this nonlinear space exists, this manifold, and we need to learn it from data. So there are techniques for this. So here's the pipeline for this. The first step, you assume that your data lies on this specific nonlinear space. Second thing, you also assume that, you do have a few samples in your database, and you assume that they belong to this space that you want to estimate. So the first step it's the first one for the algorithm. You try to build a neighborhood, a graph that links these cases all together. And the last step is you try to, flatten is not the right term, but it's very illustrative. You try to find the low-dimensional representation that is kind of representing this nonlinear space in a better way, into which you can do Euclidean standard statistics. So the two steps are like, I'll use these notations. X are my initial high-dimensional data, and Y are my low-dimensional data. And I'll first focus in the embedding step up to this low-dimensional step. Basically, it's finding a function f that maps the points x in high dimension to the points in the low dimension, with the assumption that the dimensionality is much higher before than after. So there's linear techniques to do this. The most popular one is PCA, Principal Component Analysis. What it does, it looks for the principal directions of variance into your data. So you have data of high dimension, so you are able to build a covariance matrix between your samples. And this matrix is symmetric with real values, and it can be diagonalized in this way, which means that you have P, which is a matrix of change of basis, which is convenient for going from these data, like maybe your data is in a 3D space but distributed across 2 dimensions, and you can map it with this linear mapping to these 2 dimensions into which you can do your statistics. Okay, so very popular, very simple, and the first way to start before going more complex. There's variants of it or other algorithms to go further. Sometimes you may not have some assumptions that are made in PCA. Your variables may be independent. Your variables may be non-Gaussian. And for example, if you have these kind of observations, maybe with PCA you'll still look for the principal directions of variance in this data, and you'll end up with this representation, which is not very convenient for what you like to do. While with independent component analysis, you'll find actually the directions of these clouds that are much more suited for going statistics afterwards. Okay? And to go further, there are other techniques still linear that are very convenient. PCA works, for example, when you have one descriptor of high dimension, but you may want, and it looks for the variance, it maximizes the variance on your data. But you may have a look also at partial least squares or canonical correlation analysis, which may take several high-dimensional descriptors before and try to maximize either the covariance between these descriptors or the correlation between these descriptors. So these are rather old techniques, but still very useful. So imagine you have these 2 descriptors that are, I've colored the points according to the supposed relation. So a point that is according to the first descriptor in black should be ideally also black in the other point. Like the black point here is the same as here. If I do PCA on these 2 descriptors, so basically independently, okay, I have 2 clouds that are interesting, but you see that the coloring of these points is not very consistent between the 2. Naturally, I've done this independently between the 2 points. While if I use these 2 techniques, you have maybe the embedding is a bit less better, even if it's quite an easy case, but you see that there's consistency between the 2 representation you obtain between the 2 descriptors. The coloring is very consistent across the 2. Okay? So some examples that are a bit old, but still topical. In cardiac applications, people have tried to construct an atlas of normal velocities, basically by doing PCA on myocardial velocities that were aligned. So if you look at the variations in terms of space and time, you may have a look of what is an average motion of the heart, what are the main variations of the cardiac motion. The same can be done for doing a statistical analysis of shapes, like doing what is the average shape of the heart and what are the main variations across the first direction of variation, the second mode of variation, etc. Okay? So in this case, PCA was not directly performed on the shape, but on some velocity fields that were obtained from image registration, from shape registration, sorry. Okay, so to start with, linear, but I've spent a bit of time of showing you that we should think also nonlinear, so I'll show you some examples of techniques that try to find a low-dimensional embedding with nonlinear. So a very popular one is ISOMAP, which is from 2000. The basic idea is it's very intuitive. It tries to consider the data. So here's a toy example. It tries to approximate the shortest path on your data space. So basically the geodesic distance between pairs of points. So if you see, like, if I have these 2 points I want to compare, I want to have a distance between the 2 points. The Euclidean distance is a short circuit to my graph. It goes out of my space and it's wrong. While if I consider the geodesic distance, like the shortest path along the graph, then it's correct. So what does isomap? It first computes a graph, a neighborhood graph that links each sample to its closest nearest neighbors. Okay? And then it looks for the shortest path to go from this point to these points across the graph. So the same here. To go to here, it has built a graph and it tries to follow this graph. And the second step, there's dimensionality reduction to find this kind of representation where basically the shortest path along the graph, my geodesic distance, approximates at most my Euclidean distance. So the red curve tries to look as much as possible as the blue straight line, which is my Euclidean distance. So I'm sorry I didn't put the equation about this, but basically the way to do this is you compute an affinity matrix, which is your matrix of geodesic distance, that you diagonalize, and then you have it. So some parameters about this. A key parameter is basically the number of neighbors you use to build your neighborhood graph. So on this toy example, my input data, high dimensional, is in 3D, and my embedding is actually 2D. It's just a spiral. So you see that with a few neighbors in my graph, 5 neighbors, I already have a representation that kind of resembles my ground truth embedding, which is not bad. And obviously, if I increase my connections, if I increase the quality of my neighborhood graph, so if I increase the number of neighbors, I try to get better and better with k equal 8 or k equals 13. Up to the point where my next neighbor I'm considering into my neighborhood graph introduce a short circuit. So you see that here, I'm linking a light blue with a dark red, which is probably these 2 points that have made this short circuit. Okay? So the key point is finding the optimal number of neighbors to have a good graph, a good quality graph, but without having short circuits. So some examples. We've used this to represent patterns of abnormal motion I've shown you before. So here each map is the motion in time and space of a given subject. And we found this kind of embedding up to which we can navigate to see the evolution of a given subject from normality, so this kind of map, to disease. And we can see the main characteristics of a given disease we may want to study. This was also used in brain studies, for example, to represent the brain data before doing some processing to try to find an embedding, like here you have the average brain within the population and the different variations of brain images across this population. And maybe this space, which is linear, is convenient then to do some regression, for example, with age, with risk factors, etc. As it's all linear, then it facilitates the further statistical steps. Another algorithm from this big family of manifold learning is Laplacian eigenmaps, which is also from 2000, quite old. Basically, so there's an animated view on this. Sorry, it's not moving. It looks for the main vibration, the main modes of vibrations of your data space. So here, if it was if it would have been moving, you would have seen a big vibration, and on the bottom, like the second harmonic, another kind of variation to it. Okay, so basically, it looks for it considers this. So L is called the graph Laplacian. It represents the vibrations over your data space. So I'll first start with the intuitive way into which it's constructed, which is this equation. So remember, we look for the low dimensional coordinates y. yi for sample I, yj for sample j. So we would like to, like if two coordinates in the low dimensional space are supposed to be close, 2 points in the low dimensional space are supposed to be close, this is supposed to be close to 0. So to have this very important in the minimization, you need to have this coefficient very high. And basically this coefficient is related to this, to the closeness of the data in your input space. So you have a Gaussian kernel to your data. So if two samples are close in the input space, Wij equals 1, which means this term has a lot of influence in the minimization, and the output coordinates will be close. On the contrary, if we have input data that are quite distant, that are quite far, this is quite high, the exponential is quite close to 0, so the coefficient equals 0, and then we don't really try to have close points in the output space. Okay? So it can be reformulated as this matrix problem with the constraints that is here. I'll maybe explain this a bit better. But basically you see that this is a symmetric matrix, and again there's a diagonalization process to find the main modes of vibration out of this. So some examples with medical applications. The first one is not medical. It's a very old publication from 1983 where people used optical imaging, interferometry, to see the modes of vibration of, for example, a rectangular plate. Like this is just by imaging, you see the main modes of variation, main modes of vibration of a metal plate. And the same for a more complex shape, which is, for example, not a rectangular shape, but a body-sized plate. You see much more complex modes of vibration. And this was used, for example, in brain applications to find an embedding, so the main modes of variation, of vibration, of representation of your data that, for example, explain the connectome, so the brain structure. So first mode of variation, second mode of variation, etc. Just a warning, if you want to use it, it's not that straightforward because it's highly influenced by the spread of your data. So here's a toy example. I picked a spiral and I varied the height of the spiral and its length. And you see that if the spiral is well dimensioned, if the height and the length of the spiral are quite balanced, well, the first two dimensions, so this one and this one, kind of represent correctly the 2D structure of my spiral. While if I have a high length, so this, compared to the height, sorry, I did a mistake here. So if I have a high length, I have the first two harmonics, the first two modes of vibrations are around the length that you observe here. While the third one, the third coordinates, is the one I want to focus on. So a careful thing is, and you don't really know this on real data applications, but your main modes of vibration may not be 1, 2, 3, and you may take care of this. I won't go into this, but there are algorithms to be more robust to real-life applications, into which your samples are not uniformly distributed, but you may have non-uniform distribution of the samples. And here is a family of very interesting algorithms to kind of be robust to these changes in the density of the samples. So I pass this. And actually there's many algorithms to perform this. So a very nice review, you see it's quite old because it was previous generation before deep learning. Many algorithms that try to find a low dimensional embedding that suits your application needs. And you see as a reminder that this highly depends on your knowledge on the data and your objectives. Basically, do you want to compute distances in the low-dimensional space or not. So as there are many algorithms, did people investigate the similarities between these algorithms? Is there a unified framework for this? Actually, yes. So you see that all of them are interested in building a graph between the samples. My input samples, a graph with different weights across the edges. So basically, they build an affinity matrix between the samples. If I take row I and column j, it represents how close my subject I is close to my subject j. So these matrices are symmetric, and all these algorithms involve then a diagonalization of these matrices. So there's a diagonalization process. And you see that, for example, PCA, what you try to look for is the main modes of variation. Your object of interest is the covariance matrix, which you diagonalize. If you look for Laplacian eigenmaps, your object of interest is the graph Laplacian, and it's the one that is involved in the diagonalization. Isomap considers the geodesic distance matrix, which is the one that is diagonalized. And finally, another algorithm I didn't present, local linear embedding, also looks for the affinities between the nearest samples, which is involved in a matrix that is diagonalized here. So there's a lot of similarity in it. And there are several reviews or papers that try to tend to this unified framework. I like this one, which is in PAMI in 2007. I like this one because it's very close from the Laplacian eigenmaps formulation I've presented before, which is basically the same equation as before. Basically what they say is that every of these manifold learning algorithm can be related to this formula. And they propose a way for supervised learning with graph embedding, which is basically a constraint, which is this one. You have another affinity between the samples that tries to penalize the fact that samples do not belong to the same class. So you have on one side a weight, which is this one, that tries to have the samples that are close before they should be close together after, and a penalty, which is kind of a penalty graph that tries to separate the two classes. So this is the formulation for supervised graph embedding. And here's the formulation for unsupervised graph embedding. With these constraints, I didn't talk before, which tries to keep the consistency into the data. I won't enter into detail, but if you analyze this, it penalizes the fact that some of the points explode to zero or to the infinite. So basically, it considers some sums over the weights matrix. So as a conclusion, yes, there is a unified framework for this. Many techniques with different properties, but they are unified. So back to our pipeline. We know how to do the embedding. We know how to get this low-dimensional representation with these specific statistical properties. What about reconstruction? And reconstruction is basically doing the opposite, going from your low-dimensional data to the high-dimensional data and finding this mapping. So sometimes there's an analytical formula, so we are lucky. In PCA, we have a linear change of basis to go from one side to the other. And it just considers the matrix P that is involved in diagonalizing the covariance matrix. In many cases, you don't have this analytical formula, and it's called the out-of-sample extension. And you may address this by interpolation. Okay, so you may do nonlinear interpolation between your input space and your output space, or backwards. But there's still some approximations. So some examples for this. If you navigate, so here is an embedding that represents an infarct population that we've got from our collaborators in Saint-Étienne. So this is the space of infarcts that were in our database. So again, if you compute the average of all the infarcts, you do a standard average, you have this, which is a spread infarct, which is not really a realistic infarct. Well, if you do regression, if you properly reconstruct your data from the low dimensional to the high dimensional space, you can navigate across the main dimensions of your data, and you may see that, for example, the evolution of infarcts across the first dimension, the second dimension, etc. Okay? So it's not fully binary. Your infarcts may have been binary before, and there's still a bit of reconstruction errors due to the interpolation, but still it's a guess for this. And then came the autoencoders. So they may be explained further in the summer school, but just to give you an overview of this, they have the advantage that they actually target a very good reconstruction of your data from this low dimensional space, with the difference that this latent space, this low dimensional space, may not be exactly the same as in manifold learning. So basically we can say that the autoencoders are kind of unsupervised learning on your data, but formulated as a regression, as a supervised learning. So they are quite old, from very famous people in deep learning applications. And basically, they try to look for an optimal representation, a latent space, an intermediate space. And at the meantime, they want to learn simultaneously, so in a supervised manner, the encoding step, so the mapping from the high dimension to the low dimension, and the decoder. So the reconstruction should be near perfect when you use this. Okay? So the supervision in this is basically that you try to minimize the reconstruction error in your data. The disadvantage is that there's not so much statistical properties in this, so you don't know exactly the statistical meaning of your latent space. You may have very, very good reconstructions, but then it depends on your application. You may not have this exploitation of distances in the low dimensional space. So some extensions, people have looked for very interesting extensions of the autoencoders, among which, for example, the variational autoencoders that constrain the latent space, so the low dimensional representation, to have a specific statistical distribution which may be interesting. Very popular ones are the generative adversarial networks. So I hope and they will be shown in another presentation. You may have seen this very popular example where people had a database of many, many faces of celebrities, and then they use this to generate new faces of plausible celebrities. And you look at the photo, I'm not very aware of who is famous or not, and I look at this and say, oh, maybe plausible, okay? So as a summary for the unsupervised learning part, a very quick summary of this. Unsupervised may be useful. Basically, it depends on the way you think of your data problem. Do you have labels, or do you trust your labels or not? So it depends on your data problem. Labels, no labels. It depends on your initial question. Do I want to do clustering? Do I want to detect outliers? And we've seen that the key is to learn a representation for your data, a better data space, considering that data may lie into a linear space, or there may be nonlinearities involved. And basically it depends on your objectives. For manifold learning, your embedding provides meaningful distances in terms of statistics between the input samples. The distances, they try to resemble the Euclidean distance between the output coordinates. But the reconstruction may be problematic. The autoencoders, they have very good encoding and decoding, they have very good reconstruction, but then, for the moment, they have limited statistical meaning of the latent space. Then, a quick teaser of what goes afterwards. It's a validation of these techniques, and validating supervised techniques may be straightforward, not unsupervised, because we don't have any labels. So basically, there's several hints for this. Think about the way your low-dimensional embedding works. Do you, for example, introduce a short circuit or not? Think about your application objectives. Do you want to minimize, to maximize risks between clusters? Do you want to discover knowledge? There may be hints for this. And I'll conclude with saying that for the moment they are a bit underused, and supervised learning may be a bit more used against supervised learning. And keep in mind that there's intermediate approaches that try to combine the assets of having many data, so unsupervised, but not necessarily labeled, and some labels, which is semi-supervised learning. So many people try to focus on this. Okay, so thank you for your attention. And I'll leave the speech to Carole or Rémi on the evaluation part.
Yeah, maybe thanks a lot. Sorry, Nicolas. We may have time for a few questions. So, no questions? Oh, okay.
In the Gaussian mixture, what's the difference with a real fit with two Gaussians? Do you have an idea? If you have a spectrum and a 1D spectrum, and you would do a Gaussian mixture approach, what would be the difference between a fit, totally random, not random, but I mean totally common fit for with two Gaussians that you initiate?
So if I come back to the example, maybe it's easier. I hope it's going fast. Yeah, so if I understood correctly, you say, these are my data, and what if I kind of manually fit two Gaussians to it, or, but here the point is that you learn it from data. So it should be optimized to your data. So the fit should be, according to your criterion you want to have, it should be the optimal one with respect to your manual fitting, or I don't know if I'm...
It's okay, no? Other questions?
Okay, I'm back. So we are coming to the fourth part of our presentation now. We are going to look at the method to evaluate the performance of your models. So it will be a short presentation. So to recall, and I will first start to speak about how to evaluate the supervised learning algorithm. Then Nicolas will come back and explain the part regarding unsupervised learning. So this is just one slide of this morning presentation. This morning we focus, as I said, on learning the decision function. And we say, okay, we want to focus. We assume that we have what we call the training data set. And we want to model our decision function. That means estimating the parameter θ1 and so on. So now for the rest of the afternoon, I think you have anything, you understood everything about this part. So now we will focus on the remaining part of this slide. So we want to define now how to correctly evaluate. Once we have trained our model, we want to evaluate if it's a good or bad model. So first thing, we will discuss about how we can split our sample data set As this morning I said, we have to split this sample data set into 3 parts: a training database, a validation one, and a test data set. And all what we focused on this morning was training the model on the training data set. Then I say, once you have trained your model, you want to evaluate the performance of your model on a validation data set. And as I said, this will give you some performance corresponding to one hyperparameter set θ2. Then you will choose θ2, you will change it, retrain your model, get another model, evaluate the performance of this model again on the validation data set. And once you have set the optimal hyperparameter set θ2, you can finally evaluate the performance of your best model on the test data set here. So the question is, now, how can we correctly evaluate the performance of our model, considering that we don't have access to the whole distribution of the data we can have? We have a limited range of samples, and we want to provide a good evaluation. This morning I talked about the generalization error. I said, okay, if you have only a restricted number of samples, you can estimate what we call the empirical error on the training data set. And as I said, if you do that, you can always train your model to get a training error, an error on the training data set that will be close to 0. And that means you will overfit your data. That's why you are using a validation data set. That means some other data that you have never used during your training, that have never seen your model, and that will allow you to evaluate some performance on a new data set. And what you want at the best is to evaluate the error you will have on the whole distribution of the data. So what we call the generalization data, which is representative of the whole distribution of your data. So meaning that it's different from the training database. So we want to have the best estimate of what we call this generalization error. And we have to decide when we are starting from a restricted number of n samples, we have to decide what performance metric should I use. Because I said I want to evaluate the performance of my model. So what does it mean? What performance should I use? Criterion. And also, what method should I develop to evaluate this generalization performance? So first we start by looking at some metrics, standard metrics, to evaluate the performance of supervised classification models. So suppose my task is to classify, as we say this morning, my task is to classify some pixel, for instance, to say this is a lesion pixel, this is a normal pixel, as we said this morning, a very standard classification task. So in this case, when you have your image, when you have you can evaluate if your model performed correctly. You can define what we call a confusion matrix. So suppose you have some sample data that goes through your model. You have some sample data where you know the expected outcome, considering here, for instance, a binary classification task. You have some negative and some positive sample. And here are the corresponding outputs of your system, predicted output of your system. So when your system, when your true class was negative and your system output a negative class, then you have a correct answer. Your system doesn't perform any error. So in these bins of the matrix, you will count the number of samples that were correctly classified as belonging to the negative class. It's called the true negative. Okay? The corresponding correct error for the positive case is reported in this area. It's called the true positive area. And the other two here, bins, correspond to the error you are doing. For instance, when your true class was negative and you estimate, your model estimate a positive class, you will have what we call a false positive detection. So you consider that it's a positive lesion, whereas it's a normal tissue, for instance. So the best one criteria you want to optimize is, at best, you will have 0 value here on in these two bins, and all the concentration of your answer on these two ones. So this is one way of representing the performance of your system. And you can extract some metrics from this data. So for instance, you can extract what we call the sensitivity. So it's a fraction of true positive answer. So it's a ratio here of the true positive over whole correct positive value. For instance, it's the ratio. Sorry, it's the ratio here of this. For the positive, sorry, of true positive over the sum here of the positive answer. You can have also correspondingly the specificity, which is the fraction of true negative, which is a ratio of the true negative over all the negative samples of your data. And then you can have what we call the accuracy. It's a fraction of correct answer. That means expected the true positives that were correctly reported at positive and the true negatives that were correctly reported as negative. So it's reported like that. So these metrics are very extensively used to evaluate the classification performance again in a system where you have supervised classification metrics. But as we say, in this situation, as I said this morning, sometimes what you estimate is a decision function, a scoring. For instance, the distance to the hyperplane. You don't have access to the... you have to then implement what we call the decision function to determine the class of your sample. And in fact, so sorry for this. So what we say this morning is, for instance, again, taking a linear classifier here in this classification process, you will output here linear separation that will, based on this value, you will decide, for instance, this will determine the true positive and false positive case. But in some situation, this line may not perfectly fit the physician need. And another way to consider this problem is to shift here the decision hyperplane. And depending on this shift, you will modify the value of the true positive and false positive case, as you can see here. So another metric that is usually used, instead of computing one point, here, I mean, for instance, sensitivity and specificity, is by moving here the position here of the hyperplanes, so shifting the B value here that correspond to the bias of the linear model here. By moving this value, the B value, you will change the corresponding couple of sensitivity and positivity. And you can plot such a curve that is called ROC curve, and that will allow you to see how the sensitivity and specificity varies as a function of this B value here. And for instance, in some specific case, in the medical domain, the physician may prefer having some specific points here on the curve, corresponding, for instance, by giving more weight to the sensitivity than to the specificity of the system, than what you will get from a standard SVM. So based on the original weight on the original B that you can compute for the USVM value. So these ROC curves are rarely used in the medical domain area. And usually, we can extract the area under the curve, so the notation is AUC, that can give you an estimate, a global estimate of the performance of your system without having to consider any specific threshold here, okay, to getting rid of the specific value of the threshold on the curve. So this metric, the area under the curve, you can find it, it's very often used in the medical literature. Just an extension, so here I considered only the binary classification case, but you can extend the confusion matrix case to the multi-class classification problem. and also consider the other metrics like accuracy, and you have also the other metric in the situation of multi-class classification. You have also specific, so here I considered only specific metrics for the classification. So I say I want to evaluate the classification errors. You can also have specific metrics for the case of segmentation, for instance. So here, for instance, if my original reference is S and my segmented, so the segmentation predicted by the model is T, you see that I don't have a good overlap for this segmentation. So one metric that is really used in this domain is to use what we call the dice index that evaluates the ratio of the intersection between the reference and the estimated segmentation over the union of the two. And you also can have another, sorry, I forgot to mention, another metrics, for instance. It's not an exhaustive list, but some other metrics like the Hausdorff distance, which will estimate the largest distance of both areas, S and T, to the other elements. So it's another way of evaluating another metric of performance specific to the case of segmentation. So when you have defined what the metrics you want to do, now the second question, the second thing to do is how will I evaluate the performance of my model, considering that I have a limited number of samples. Okay. So there are different methods of evaluation. The first one is referred to as what we say the holdout method. It means in this situation, if you have n samples, what it will do, it will learn the model on your n samples and test your model on the same sample data set. So meaning that the training and the evaluation and even the test data set are equal. So what do you think of this strategy? As I said this morning, if you train your model on you may be prone to overfit your data. So this model is very easy to implement, but also, I'm sorry, I made a mistake. I was speaking about the resubstitution model, but it's a holdout here, so sorry. So no, the holdout, sorry. Erase everything I've done before. So for this model, you will split your data sets into two parts, separate parts, train your model on one part, and evaluate your model on the other part. So there is no mixing on the model. So you do it once. So the problem, so it's perfect because in this situation, the data that you will test your model on have never been used to train the model. So you don't overfit, contrary to what I said. This schematic is very easy to implement. There is a low computational weight because you have to train only one model on your training data and test it on the validation set. But the bottleneck is that if you have a very limited number of samples, it's very difficult to decide to make the split between what you will use to train and what you will use to test. So it generally can work well if you have a lot of data, so a lot of data. And also it's sensitive to the way you split your data into two parts, in the training and splitting database. So this method is generally not really used, depending, again, in the medical situation, because you don't have access to a very high number of data. But the other thing is that it's very easy and very quick to implement. So what we generally use in the medical domain is what we call the careful cross-validation method. In that situation, we will divide our dataset into into two parts. So into what we call different folds, so into different subsets. So the first thing you have to decide is how many subsets you want. For instance, here the number of subsets is k. So you will split your data set into k parts. You will use k minus 1 parts to learn the model, and then evaluate the performance of your system on the remaining fold. Then you will repeat this by changing at each time the subsets that you leave for testing, and you will combine the performance that you achieved on the different folds that were left apart during the training. And suppose you choose k equal to n, where n is the size of your data sets. So it means if you have a data set of n samples, you will train your model on n minus 1 samples, and then evaluate your model on the remaining sample. So it's called what we call the leave one out. So you leave one sample out for the training. It's called the leave one out validation metric. So here it's a schematic of what I've just said. So suppose you have your training data set here. So what here, for instance, I chose a six-fold validation, cross-validation. So I will first learn on this fifth subset here, learn my model, then test it for the remaining subset. And I will jump to the next step by choosing another subset of training folds here, train the model, and test it on the remaining one. And by combining all this evaluation, I will have an estimation of the performance of my system. So the advantage of this system is that it's easy to implement first, and it will make use of all the available data, contrary to the holdout model that we have seen previously, where here all the available data are used to train and to evaluate the model performance. Sorry, it's in French. One of the limits is that it may be sensitive to the splitting strategy, and also it's quite heavy to compute. Why is it heavy to compute compared to the previous model? Okay, yeah. If you decide, because you have to, each time you take a subfold here, you have to retrain to learn your model. So depending on the time it takes to learn your model, so you have to do it k times. So if you decide to use a leave one out validation procedure, then if your sample data set is big, then it will take very long time to each time learn the model and do it. So it's quite an easy procedure. And also, it doesn't provide a final model, because each time I train the model here, I will get a tuning of my parameter, θ1, for this model. I will evaluate the performance on this model 1. But this model 1 here that is learned will may be different from this model here that is different. So with this procedure, I will have an estimation of the performance I can get from the model, but I will not have one model, okay? Because each time I will get a different model. So it's just a way to estimate the generalization performance that you can have. Another method that can be used is called the Bootstrap method to evaluate the performance of your system. In that situation, so suppose you have a data set of n samples again, you will draw what we call a bootstrap sample by randomly sampling the same number of samples. So if you have n samples in your original data set, you will randomly draw n samples with replacement from your original data. It will provide you what I called XB here, this sample data set. So here and here it's the same thing, okay? I just try to make some words. So then once you have your XB, your bootstrap sample here, you will evaluate the performance of your system by learning on XB and testing on XB. So here I made the performance metric I use here is the area under the curve, but it can be anything you want. And here, this formulation is what I talked about a little bit earlier, is when you do resubstitution, meaning I learned the model on one data set, and I evaluate it on the same data set. What is the risk of doing that? We call that resubstitution. When I learn, when I train and evaluate on the same data set. It's overfitting, and it will give me a performance that is optimistically biased. Okay, so I know that this is biased. Okay, and what I want to evaluate by doing that is evaluating the bias I'm doing with this method. So I will repeat that. So I will have to choose a number of bootstrap samples I want to do, like this B value. I will repeat this, so draw my bootstrap sample, evaluate the performance by resubstitution, and also evaluate the performance by learning on XB and evaluating on the original sample, okay, here. And by taking the difference here of these two terms, I will have an estimation of the bias. Then by getting the average of this bias, I will then try to estimate the performance. Now I'm doing the evaluation of the performance by resubstitution, but on my original sample here. So learning on X, testing on X. But I'm subtracting the bias I have estimated previously. And this gives you, again, an estimation of the performance I will get on the general population. So as for the previous method, this is quite easy to implement. It also makes use of all the available data. And also it can provide me confidence intervals here, because I can get a value on the metric I get. But as for the previous model, it's kind of heavy, because I have each time to redraw some bootstrap sample. I have to relearn my model and evaluate the performance. And like for the cross-validation model, it also doesn't provide a final model of my system. And again, for me, I think it's everything I wanted to tell you. So do you have specific question on this part?
Sorry, maybe I misunderstood, but I don't exactly get the point of using a bootstrap method or k-fold, since at the end you cannot have a final model that you can use for inference, for example. What exactly are you doing with this number of accuracy, for example, coming from a k-fold if you don't have a final product?
It's used for the validation, during the validation step. Okay, just to maybe optimize your parameter, your hyperparameter θ2 that you have. So it's a way of best using the performance, best using all the data you have, but it's the data combining the training and the validation data, in fact. And then you can decide, once you have selected the best hyperparameter set, you can retrain your model, the whole model with this hyperparameter set, and then test it on the test data set. Okay, but it's generally used for the tuning of the hyperparameter set.
Other questions? And for the previous presentation also? No? I have one question for Carol. If
yes.
You don't have discussed, but about the recommendation you can do about the size of the sets for using scaffold or for making some validation. For example, if I have 100 samples, what are you recommending for making a correct validation using for training? I don't know if there is some values. 80% is enough, 20% is in.
I mean, there is no real rule. It depends really on your data, but yeah, usually you shouldn't train on, you should make use of most of the data for the training and then try to evaluate on
Okay. Even if there is the compromise with overfitting?
Yeah, it's always a compromise, but there is no golden rule, I guess.
Okay, no golden rule. Okay, thanks a lot. And come back to Nicolas if there is no more questions.
Okay, so I'll try to be light because coffee is coming. But I'll pursue on the supervised version of the evaluation of your models. So unsupervised, we've seen that there's no ground truth labels, so that's not so easy to validate. And I'll go through some practical examples to show you ways we've validated some unsupervised embeddings. But obviously, it highly depends on the data and your clinical question. So these are some hints for your data. So the first one, I've spent some time showing that in many unsupervised approaches, there's a neighborhood graph that is built. And if you do it wrongly, in some cases, you may introduce some short circuits. So in synthetic data, in this example, that was quite easy to see. When a short circuit was introduced in the data, basically you lose the embedding. There's a lot of changes from one dimension to another. So in this case, you may want to use a metric that traduces this. So you may want to compute the error you're doing with respect to the approximation of the distance you want to estimate. So if you want to estimate the geodesic distance, let's compute the error between my path here and my straight line here, okay? And basically you see that when you increase the number of neighbors, this error decreases. So you're getting better, better, and better, close to zero, up to you introduce a short circuit, and then it explodes. But that's quite easy because it's a very synthetic example for which you know ground truth. So in real data, it's unknown. And here's a hint for doing this. You may want to compute something that is called the node flow on your graph. So what it means is like you try to accumulate up to your graph. You try to count the number of shortest paths. You pick an edge, on your graph. You give an edge between 2 points. And you try to count the amount of shortest path that's passed through this edge. So visually, what it means. I'll start on the right. If you have something that is distributed like this, and the dots are colored according to this measure or node flow, you see that there's a lot of shortest path that pass through this very straight line. Obviously, to go from here to here, you have a shortest path that goes here, okay? So it's very easy to spot. It's very easy to spot like kind of your distribution of your samples in this embedding. While when your data is more distributed, it's kind of uniform distribution of the node flow. So what happens when there's a short circuit? Kind of uniform distribution, more or less. So the node flow is not so high. But when you have a short circuit, many shortest paths pass through these points. So if I do a zoom, you see that there's a point that is very reddish with a lot of shortest paths that goes to this point. So it's easy to spot here that the measure explodes when you introduce a short circuit, and this may be interesting for your real data validation. So here is something we've obtained on real data, the computation of the node flow with the increasing number of neighbors. And it seems that on this data, there's no short circuits. The measure tends to something of saying that all my data are connected, but I couldn't spot any short circuit. Does it mean I'm validating this? No, it does just mean that my space is maybe too complex for this kind of measure. So still unknown. Then the key question is you look for a space of lower dimensionality. So what is exactly the dimensionality of my data or the exact amount of clusters I may want to have? So again, synthetic example, dimensionality of the input is 3, but it's a 2D space. And in this very simple case, I have exactly 3 relevant clusters. How to do this in practice? So on real data, you may also want to look for, again, the error of the embedding. So you may want to vary the amount of dimensions from 1, 2, 3, etc. The more dimensions you have, the error with the measure that is related to your embedding. So this was the isomap algorithm. So the error was against the geodesic distance. So you see that this is the brain application I've shown you. They found that after 3 dimensions, it seems that this error tends to stabilize, and maybe with 3 dimensions, it's quite enough. We've done also the same on the cardiac application with varying number of neighbors and varying number of dimensions. And it seems with few number of dimensions, we're quite okay for this kind of application. But still, it's not fully known. So there's some measures that may help, or at least better understanding the behavior of your data. There's a measure of compactness. I'll show you afterwards. Compactness means the decrease in the eigenvalues computed, or the increase in the reconstruction error when you add more and more dimensions. Okay, so if a representation is compact, you have a lot of information in the first dimensions and not so much afterwards. Another measure is the generalization ability. I'll show you afterwards. You pick one case out of your data and you look, as Carol said for the Lyon procedure, you look for the error in reconstructing this case. So that's my model. Is my model able to reconstruct this case? And the specificity is I'm generating new cases randomly from my low-dimensional coordinates. Are these cases physiologically plausible, or are these cases plausible? Do they resemble my input data? So you could build some kind of graphs like this. You vary your number of dimensions, and you look at the 3 measures: the compactness, the generalization ability, and the specificity. For example, specificity, these are 3 samples that I'm generating with PCA. I'm generating them randomly in my Euclidean space, and obviously they are out of my manifold, so they do not resemble any data. There's bad specificity. While if my model is well fitted, all the data I will generate will be around this straight line, and I would be able with this measure to say, okay, my model is enough. On real data, it's a bit complicated still. So with unsupervised data, what you could do is imagine you want to distribute your data, but still you may have some clinical information that you don't want to use it for supervised learning, but you want to use it to see if your low-dimensional embedding has some meaning. So you may look for clusters in your unsupervised space and see how do you agree with existing labels across the dimensions. So for agreement between populations, the measure is the kappa index. You may also increase your number of dimensions and see if your low-dimensional embedding changes when you add more and more and more dimensions. So if you increase from 2 dimensions to 4, 5, 10, etc., do you reach a stable embedding that does not vary so much when you add more dimensions? So these are some hints on real data. The same for the clusters. You have this space that doesn't look really partitioned. And what happens if you take 3 clusters, 4 clusters, 8 clusters? First question, are your clusters kind of consistent from one step to another? If I had the blue cluster that came on the right side of the figure, then I would have been in trouble. And then you may want to look at the consistency of your initial data, your clinical data, within the clusters. So with 3 clusters, here's my data distribution. It seems that, for example, the green cluster has a higher proportion of ischemic cases and a wider QRS complex. But it seems that when I use 8 clusters, it seems that it's also the case for the green cluster. So there's kind of consistency across my clusters distribution. Okay, so this is very application oriented, but this gives you some hints it's not really validation, but kind of having the feeling that it's not doing rubbish. If your objective is risk stratification across your population, you may want to see what is the risk associated to each of your clusters. And if, for example, with 4 clusters, you have one cluster that is really at high risk, and this is consistent with the amount of clusters, maybe your conclusion is not we did spot 5 or 6 clusters, but your conclusion would be we spotted a high-risk cluster of patients. That is the interesting thing. Okay, so this is, again, very application-oriented. And as Carol said, it's better to have part of your data for training and see the consistency when you generalize your model on a validation database. Do I still have this, for example, high-risk cluster, both on my training and validation data? And then the initial question also was, is my data evolving around a linear space or nonlinear space? So what you may do is try to reconstruct your data from your low-dimensional space to your high-dimensional space, and look if your data are physiologically consistent. So here, the pattern I was studying was this kind of abnormality of blue and red spots. Okay, all my population, if I show you many cases, they were like this, blue and red spots, varying in temporal distribution and spatial distribution. So when reconstructing many cases from my low-dimensional embedding, with the nonlinear technique, I have always this kind of signature of my pathology, meaning that it seems that I'm behaving well on my nonlinear space. While you see when I'm doing with the linear technique for embedding, maybe it's okay on the first dimension. It looks like a physiologically plausible signature, but on the second dimension, you see that blue, red, blue signature that is, I'm going out of my space, I'm getting wrong with the linear techniques. Okay? And then you may also have a look, apart from the physiological consistency of reconstructing cases, you may have a look at the relation with, for example, risk or the distribution of your data. This is very application specific, but what is your organization of data if you do nonlinear or linear techniques? Is one messy with respect to the other, or don't you have the answer of this? Okay, so as general conclusions, I'm taking the message for the whole set of us. So the take-home message is that we have a lot of techniques for supervised and unsupervised learning. We're lucky because they are able to handle complex data, and actually Carol showed us that for medical imaging, data are complex. We have many data, but not so much. High-dimensional data of multiple types with specific physiological properties, so it's quite complex. The key point to start with is really think of the definition of your problem, but with respect to the application. Do you want to do classification? Do you want to do clustering? Outliers detection, etc. Evaluation is key, but it's not so easy. It's easier when you have labels. And I'll insist on this. There's a trend in computer vision, but not so much in medical imaging, of transparency. So there's more and more open code that is published and open data. So you may have been aware of challenges such as Kaggle, or challenges that are more and more organized in medical congresses. So just participate to this. It's fun, and you get in touch with more and more data and learn more things. So some conclusions specific to medical imaging applications. Well, why doing machine learning? It's first to go beyond the standard learning with simple statistics. But we should always first start with statistics, see the limits of them, and then try to bring to more complex models from machine learnings. And we should never forget the specificities of medical data, which is a big difference with computer vision applications. Data are in high dimension, but with specific properties. So here I've said tensor properties, but maybe physiology, which is not so much considered, etc. So this opens two challenges, and luckily we have some work for the next years. So something that is rising is the field of semi-supervised learning, taking advantage of few annotations and many not annotated data. The mixing of many descriptors of different types, so multiple, high-dimensional, heterogeneous descriptors. And then some specific warning and fields of research for medical data. Well, real-life data, they are not complete databases. So sometimes the descriptor is missing, sometimes the descriptor is of bad quality. Sometimes you don't have thousands of cases or millions of cases. So we should bring shortcuts from research to cope with this. We didn't talk about adding priors that constrain the observations to physiology, but that's an active field of research. If you do a segmentation, it may stick to the image, but it may not be physiologically consistent to a heart shape or a brain shape. So there's a field of adding priors to your data. And we didn't talk about uncertainties, but we're all building models about your data. Some models may be more accurate or not, but they're still uncertain about your data, and they may still explain part of your data. So what are the consequences of your uncertainties, and are you able to estimate them? That's a key question also for the future. So thanks a lot, and we're open to questions or coffee.
Thanks a lot, Nicolas. Is there some questions about these approaches?
So I have a question which is not really related, it's more like general to machine learning. So I think normally you have training data that where most of the training data belongs to a class, so like data unbalance. So what techniques exist to so that your model is not biased by this factor, or how should you separate your training, your testing set, so that you don't have any biased model to this?
That's a very good question. You may want to answer, or it depends. Maybe you have a better answer than mine.
So your question is how to divide. Suppose you have n samples, as I showed you before. How to divide?
No, it's like, for instance, if you want to classify something, you have in your training data you have a higher part of your data that belongs to a class than the other one. Like, I think this will somehow bias your model when you are training your data.
Yeah. So when you're splitting your data set, for instance, in training validation data set, it's important to consider making a stratification. I mean, if you have, if you're doing a multi-class classification, for instance, to draw some samples of each class, trying to respect the original distribution of your data. And in some specific case, when you're very imbalanced, I mean, some class is very is less represented, then some algorithm may be robust to this class imbalance, but some are not. And there are different techniques to try to balance these different classes. So either you will generate artificial training data set by sampling the data, making some kind of getting back to a balanced data set. Or you can also do some synthesis, or what we call data augmentation. You will draw some sample from the minority class, for instance, to try to go back to the... You have other things?
Okay.
Okay, it's okay for unbalanced data? Okay, nice. Other questions?
In this last slide, you mentioned the completeness and the amount of data in real life. Are we going to go through this the missing data issue within the training process and the testing process? That's my first question. And about the amount, I noticed that you were talking about techniques to generate data that are similar to real data. Is there any solution in this way to overcome the low amount of data in real life?
Yeah, so that's a very practical and topical question. So yeah, either you fill in your missing data with plausible observations at the risk that you invent some data, so you may take this risk. So you may use the techniques I've shown to generate new samples independently on your data, but you may lose, for example, if your objective is to, for example, to mix many descriptors together and you generate some data without taking into account the others, then you might make a mistake. And so this is working on the data space. And if you remember well, some of the techniques I've presented work with kernels, affinity matrices. And instead of generating data, you may work on these kernels and try to fill in these kernels, the kernel values. So you don't consider creating plausible data, but you consider filling plausible kernel values. And this may be easier to achieve sometimes. These are two options, I would say. I don't know. Maybe a last thing. There's also a last thing people are also trying to do is also to use simulated data that supposedly matches your real data characteristics. So it's not learned by your learning that you want to evaluate. But if you have, for example, a medical imaging simulator that simulates ground truth images that resemble your real data, it may be used, for example, to fill in the missing data with some plausible data. But still, it's a risk to take.
And maybe just to finish with this point, the last thing, fashionable thing to complete your data now is to use deep learning networks like generative adversarial networks that will try to replicate also synthetic data, and you have a lot of topics of in the field to synthesize the missing data from the original one, for instance. So it's another way now to try to complete your data sets. But it's still under evaluation because you can generate fake data too. So.
And don't worry, there is one morning about GAN, generative adversarial neural networks that are able to generate such realistic data. Other questions? Yep.
Thank you. It's a question a little bit out of the field. As I understood, in supervised learning, you use images that are already labeled, for example. So in my case, it would be manually labeled by experts. And then you give this to the system to teach it how to label itself. And is there a way to understand if the machine outperformed the specialists, for example? If you have specialists that do manual labeling, which is far from being perfect in 3D images, for example, is there a way to correlate the error the experts may have done specialist annotations variance and the best result we can have with machine learning with respect to this variance in between specialists annotations?
Okay, would like to answer it. Yes, there is many works on it. And recently, there is a study about myocardial segmentation based on UNet, one deep learning architecture very useful for segmentation. And Sarah, you can answer about this part? No? Or Pierre-Marc, if you are, no?
So basically what we can do is ask experts to perform segmentations. That's how we manage to have our data sets. And from this expert. I'm coming there. From having the segmentations of several experts, you can compare them. And for instance, using the same metrics that you use for assessing your model's performance, you can get an idea of the differences you may have on a given problem if you were to ask several human beings. And then you can deduce what we call the intervariability, so the difference in between experts. And if you have a same expert doing the segmentations 2 times or several times of the same images, you can also have the intravariability. And then what we want to assess is whether our model could be not only considered, of course, as an expert, but also maybe be as close as possible from the expert it learned on. And concerning the results of our specific study on echocardiographic segmentation, we managed to see that on average the model was performant enough to be below intervariability inter-expert scores, but not close enough to intra scores. So there were still gaps for improvement. And I would like to add that this study only compared the performances on geometric metrics, so like the dice and Hausdorffs that were presented, and that these metrics may not be enough to represent the quality of segmentation. And so that's why we are also investigating other metrics, anatomical metrics, the kind of metrics that would represent what, as a human, you would assess as a quality segmentation, like overall smoothness of the contourings and such. Does that answer your question?
Quite far question from the presentations, but very interesting. Well, other questions?
Maybe I could complement.
Okay.
There's 2 things you want to assess. Just to summarize, the variance is the variance of your experts versus the variance of your algorithm, and in the meantime, what is called the bias. I maybe with a small variance, but I'm very far away from the ground truth. So these are the 2 notions now.